Early morning, November 21st. SpaceX's Booster 18, the first Super Heavy V3, stood at Massey test site undergoing routine pressure checks. No propellant loaded, no engines installed, just nitrogen and oxygen gas. Then, without warning, the lower liquid oxygen tank violently ruptured, tearing open a massive section of steel. What could cause a rocket to fail during a simple pressure test when there's no fuel involved? SpaceX has identified the culprit, and it's a problem they've seen before. But if Booster 18 is destroyed, how is another V3 already stacked in December? Here's what the security cameras captured. Pressure was climbing steadily inside Booster 18's tanks, standard procedure for this type of verification test. Engineers monitored from a safe distance when telemetry suddenly spiked. Then came the sound. Witnesses described it as a massive whoosh, followed by metal tearing. The lower liquid oxygen tank didn't explode outward like you'd expect. Instead, it looked like something punched through from inside, peeling back reinforced steel designed to handle millions of pounds of thrust. What kind of force creates that specific damage pattern? The answer lies in the chine area, that narrow section running along the booster's exterior. Inside that space sit composite overwrapped pressure vessels, or COPVs. These carbon fiber bottles store ultra-high pressure gas used to pressurize the main propellant tanks during flight, with pressures exceeding 6,000 psi. When investigators examined the wreckage, they found the COPVs in the chiny area completely shattered. The hole in the booster's side lined up precisely with where those COPVs were mounted. But one critical detail tells the real story. Look at the tear pattern in the metal. The tank wall bent inward first, before gas pressure blew it outward. That sequence means something from outside the main tank punched inward, then escaping oxygen created the catastrophic rupture. The internal transfer tube, that massive pipe running down the booster's center, shows a puncture mark like a projectile entry wound. Vapor was spotted leaking from the chine seconds before the main tank failed. Every piece of evidence points to the same conclusion. A COPV failure triggered this cascade. The physics behind this explains why the damage looks so unusual. When a COPV fails catastrophically, it releases extremely cold nitrogen in a fraction of a second. That sudden blast of cryogenic gas creates a brief vacuum effect as it rapidly cools surrounding air and pushes oxygen out of the cavity. Temperature drops. Pressure plummets. This creates what engineers call a lazy explosion. The tank looks crushed by external force rather than blown apart from within. Then comes the rebound pressure wave, devastating in a confined space like a rocket's internal structure. This explains the strange damage pattern, but it raises a bigger question. This isn't SpaceX's first COPV problem. Back in June, Ship 36 suffered a similar incident at the exact same test site. SpaceX immediately implemented new protocols after that failure. They reduced operating pressure in all COPVs, added extra inspections before loading propellant, updated acceptance criteria, and developed new non-destructive testing methods to detect internal damage. They even added external protective covers to provide visual warning if something goes wrong. Those lessons were supposed to prevent exactly what just happened to Booster 18. So why didn't they work? That's the question SpaceX isn't answering yet. The company confirmed the anomaly, but said their teams need time to investigate before they're confident of the root cause. This means they know what failed but aren't sure why their safeguards didn't prevent it. And that uncertainty matters more than the failure itself, because if the same safety improvements were in place and still failed, something else is wrong with the V3 design. The investigation will determine whether this was a one-off manufacturing defect or a systemic issue with how V3 handles COPV integration. The overnight images tell a brutal story. Booster 18 was effectively cut in half. The methane tank and integrated hot staging ring separated completely from the lower LOX tank and aft section. That massive internal transfer tube, nearly as wide as a Falcon 9 rocket, was the only thing holding the upper portion in place. The aft section sits so close to the fracture origin that it's almost certainly damaged beyond repair. Interestingly, the pipework at the bottom looks surprisingly intact. If engines had been installed, many might have survived in usable condition. But SpaceX won't bother salvaging anything. Here's why that decision makes sense. Reusing components from a failed vehicle introduces hidden risks that require retesting and recertifying every single part. That process takes longer than building new hardware. SpaceX's manufacturing capability has reached the point where building fresh is faster than salvaging damaged goods. Their philosophy is straightforward: build the next ship, fly the next ship, and that rapid production cadence is about to prove its worth in a way that should seem impossible. 3 days after the failure, SpaceX posted an update. The Starbase team plans to have the next Super Heavy booster stacked in December. Not started, not in production, stacked, meaning fully assembled and ready for testing. How does a company lose a booster on November 21st and have the replacement ready within weeks? The answer reveals SpaceX's manufacturing revolution. While Booster 18 was testing, Booster 19 was already moving down the production line. Multiple V3 vehicles are in various stages of assembly at any given time. This parallel production approach accepts that some will fail during testing rather than building one, testing it, learning, then building another. The result? A catastrophic failure in late November doesn't push back the flight schedule at all. SpaceX stated that Flight 12, the first mission using V3 hardware, remains targeted for Q1 2026. Elon Musk anticipated setbacks when he warned that Starship V3 would have teething problems due to massive upgrades it incorporates. At the Economist Space Summit on November 5th, Kiko Doru, SpaceX's VP of Launch, emphasized what's at stake. We're now super focused on the version 3 rocket that will launch early next year. That's really going to be our production rocket. V3 isn't just another iteration. It's the foundation for everything SpaceX has promised, and the upgrades explain why. The improvements are substantial. Larger propellant tanks increase total capacity. Redesigned Raptor engines deliver more thrust with better reliability. Structural improvements reduce dry mass while increasing strength. These changes enable V3 to deploy the next generation of Starlink satellites, larger, more capable units that current Starships can't handle. More critically, V3 provides the performance margins NASA requires for the Artemis lunar lander program. Without V3, SpaceX can't fulfill its $2.9 billion contract to land astronauts on the moon. The pressure is immense, and this failure adds another complication that NASA is already addressing. On October 20th, NASA Acting Administrator Jim Free stated he would open up the Artemis 3 lander contract, requesting acceleration plans from both SpaceX and Blue Origin. The message was clear: show us how you'll get back on schedule. SpaceX responded on October 30th with a proposed simplified architecture for Artemis 3, though they provided no technical details publicly. They argued that despite delays, Starship remains the fastest path to returning humans to the lunar surface. The official Artemis 3 target is 2027, but industry analysts privately suggest 2029 or 2030 is more realistic. Does this latest setback add another year to that timeline? Not necessarily. This failure happened during the exact type of test designed to find these problems before they become catastrophic during flight. No propellant was loaded, no engines were installed. The test did its job. It exposed a weak point in the safest possible environment. Kikodoru noted, as long as we fail in a way that never hurts anyone or causes an issue that drastically sets us back, it's okay to learn through testing. All 11 integrated Starship flights to date have been iterative successes in that each one taught the team something crucial. The real question is whether this COPV failure represents a contained manufacturing defect or a deeper systemic issue. That determination depends on investigation results. If this was one bad COPV that slipped through quality control, it's a contained problem. Build better, test better, move on. But if this represents a systemic issue with V3's COPV integration, or if Ship 36 fixes weren't properly applied to boosters, SpaceX has a deeper problem requiring production pauses and potential redesigns. The next few weeks will reveal everything. Booster 19 needs to pass the same test sequence that destroyed Booster 18, proving it can handle maximum pressure loads. Then comes structural proof testing with actual cryogenic propellant, engine installation, and static fire tests. Each step brings new risks and new chances to discover problems before flight. With a self-imposed Q1 2026 deadline approaching, SpaceX's ability to learn fast and adapt faster will determine whether they meet that target or face their first major schedule slip on the V3 program. So here's what this really tells us about SpaceX's approach to building the most powerful rocket ever made. Most aerospace companies would treat a failure like this as a program-stopping event. Months of investigations, board reviews, design committees, and careful analysis before moving forward. SpaceX loses a booster on November 21st and plans to stack the replacement in December. That's not recklessness. That's a completely different philosophy about how to reach orbit reliably and affordably. The traditional aerospace industry builds one rocket, tests it exhaustively, flies it, then builds another. SpaceX builds 10 at once, accepts that some will fail during ground testing, learns from each failure in days instead of months, and keeps the production line moving. This is how they've launched more rockets than any other company while simultaneously developing the most ambitious spacecraft in history. Booster 18's failure wasn't a setback. It was the test working exactly as designed, finding problems before they can hurt anyone or destroy a flight vehicle. The real story here isn't the explosion. It's what happens next. Booster 19 will go through the same tests with whatever fixes the investigation reveals. Flight 12 will still target Q1 2026. V3 will eventually enable lunar landings and massive Starlink deployments. And somewhere in Starbase right now, Booster 20 is already taking shape on the production line, because at SpaceX, there's always a next one ready. What do you think about SpaceX's rapid iteration approach? Does accepting ground failures lead to better rockets, or does it introduce risks we're not seeing yet? Drop your thoughts in the comments. If you want to stay updated on every Starship development as it happens, hit that subscribe button and turn on notifications for new space review. And if this video helped you understand what really happened to Booster 18, share it with anyone who's following the Starship program. Thanks for watching, and I'll see you in the next one.